Hello everyone, welcome to the manufacturing processes class, and today's lecture we're gonna continue the topic that we started the previous meetings, which is the sand mold design. We covered the general procedure of the sand mold design over 3 videos. Today I'm gonna give you some examples and solve some examples as a practice on the sand mold design, and as a practice how we can apply the procedure that we discussed before for example, like example one here, for to make or to cast this product. Like this is the final product, and all of these given dimension, this should be the dimension that should be provided to the customer. It means that this is the final product, and we have to come up with the complete design of the sand mold, including the pattern, the dimensions of the core and core print, the dimension of the flask, the dimensions of the gearing system, everything to make this product by casting, especially the sand casting. So it is required here to design the sand mold, required to cut the following steel product. So it is made of steel, and the design calculation should indicate the dimensions of the pattern, the dimension of the core and core print, the dimension of the flask, in addition to the dimensions of the gearing system. If you remember in the previous meetings or the previous video, we said that we are going to skip the riser design step, which is the 10th step. It means that here we are required to just apply the first 9 steps that we explained over the 3 videos before. And in addition to these dimensions, we said that the main given information that will be provided to us is the detailed dimensions of the final product. So this is the final shape of the product with all of these given dimensions. In addition, some data that would be provided, like for example the S, which was the constant that we was using for the pouring time calculation. Here it is, let us assume that it is given by 2, and let us assume that mu, which is the coefficient of friction between the molten metal and the sand, that is already given by 0.3. And you should understand or know that the density for the steel, since the product is steel, it is commonly known by the 7.8 gram per centimeter cube. So these are the given data, and again it is required to come up with a complete design of the sand mold that would be used for making this product by sand casting. So if you remember, just stick to the general procedure that we explained the previous time. The first step basically is just to draw the pattern, is to come up with a tentative shape or design of the pattern of this product. Just draw the pattern. So if I ask you how it looks like, how it's gonna look like, the pattern of this product. So to come up with the pattern shape, you should understand what is this shape, the shape of the final product in terms of engineering drawing. So generally for engineering drawing, any product that can be represented using only one projected view is the cylindrical products or cylindrical objects. Like any cylindrical object, it can be represented only using one projected view, and there is no need to 2 or 3 projections. So here we do have only one projected view of this product. It means that intuitively it should be cylindrical shape. And this is very clear from the phi that is given here. Phi indicate that this is the diameter. It means that there is a circular thing. Also here we have phi 600, phi 400, in addition to some heights. So generally any cylindrical shape, like any simple cylinder, it should have like a diameter, and the diameter, let's say like phi number, and it should have a height. So as you can see, all the dimensions that already given to us here are either heights or diameters. So it means that this shape, it should be cylindrical shape in general. But how it looks like, this is very important to understand what is the shape of this product. So if you're gonna see that we do have something with a diameter of 600, start with the big diameter to come up with the shape. In addition, there is a height of 300. So we're gonna say that we do have like a big circle with 600 diameter, and there is a height here of 300. Like we do have like a complete cylindrical shape, but there are some other details inside. There is like an internal hole here, an internal opening of 400. It means that there is something opened here, like a cavity of 400 millimeter, and it has also the same height as given here. But there is a hub in the middle. What is this hub? This hub, it has like an external diameter of 250 millimeter, and this is the hub. and there is like a small hole in the inside it, which is 50 millimeter diameter as a hole as shown here. All of these shaded region, this indicate that this is the metal part, but there is something that connects the hub. This is the hub and this is the rim. This is known as the rim, this is the exterior, and this is the hub, which is just the middle part of this wheel, because this is like a wheel that should be made of steel. All right, so and this something that already connect the hub to the rim, this should be web already given here. So this web is a blank web. It means that it fell out everywhere inside this rim. So it's gonna be, it means it's gonna look like this case. So with this part, it should be the web part that already connects the hub to the rim as given in this three-dimensional representation. All right. So these are other two representation of the same product. Again, it is like a rim. This is the exterior, which is just a rim, like a cylinder ring, and there is a hub in the middle. This is the hub part, and this is the web, which it should be connecting. It is very similar to this product, but we don't have this groove. There is something here as groove, which is this part over this surface. We don't have this one. In case that would have this groove, it should be represented in this way, like there should be like a groove here. But this part, we don't have it. We don't have this groove. It won't gonna be shaped in the casted product that we are considering in this problem. So it means that this is the typical shape. Again, there is a hub here, there is an external, which is the rim, and this should be the web, which is the something that should be in the middle here. In some cases, we would replace this web with some arms. So we're gonna have like some arms here. Okay, instead of have like a blank web, we would have some arms instead. So it means that it's gonna be the same thing. So a product with this shape, it would be like a wheel, or it would be used as a pulley in case that would have a groove like this case. So it would be used, and the objective again is just to make this product by casting. Make sense? So this is the shape for the pattern. So since we came up with like the shape of the product, how about the shape or the tentative design of the pattern itself? How it's gonna look like? This basically, it's gonna be typically the same like the product. As we discussed, there are some differences between the pattern and the product. The big difference comes in case that we do have an internal hole like this one, which is already located inside the hub. And here we are going to form this opening or this internal hole by casting, because the diameter is 50 millimeters, so it is better to make this one by casting. And this usually for this kind of product, we form these holes by casting directly, and we don't machine them using the drilling process, especially that this length, it is kind of long, somehow 300 millimeter, it is too long to have a twisted drill to open this hole. So it is advised basically to form this or open this hole by the sand casting process, and this is what we are going to do. It means that in case that we do have an opening, as we mentioned, we have to have the pattern, it should be plank without this opening, and instead we're just gonna add cool prints just to support the code that we should be applied here, that would be used for forming this hole by casting. Make sense? In addition to some other differences that related to the machining allowance, difference in terms of dimension, a little bit difference in the shape because of the taper, and this is what we're gonna do once we choose the parting surface, and this is for step 2. So basically step 1, it is very simple. You can do it very quick. Here just because I'm explaining to you, I'm taking time, but directly, if you realize what or just understand the shape of the product, you can directly come up with the tentative design and the shape of the pattern, which is very similar to the product. But the key idea, we have to get rid of the hole, and instead we're gonna apply some core prints here. So this should give us directly the pattern. So intuitively for this case, the pattern of this product will be closed, will be blank without any holes in this case, and instead we're just gonna apply some core prints here. So it means that this should be the shape of the pattern itself. Then the next step, which is step 2, is just to identify the parting surface. And we said that there are some essential requirements for the parting surface. So this is the step 2, which is the parting. Select the parting surface. The parting surface, first of all, it should be a flat surface that belongs to the pattern, and you have to investigate the parting surface from the pattern, not from the product. This is the product, but this is the tentative shape of the pattern. So the parting surface, it should be a surface of the pattern. This is one thing. And another thing, that it should be flat surface. And the key idea that when we try to remove the pattern from the sand, it shouldn't break any sand while we are removing the pattern from the sand during the molding process. So if we're gonna look to this product or even the pattern, you're gonna see that we do have a few surfaces that could be considered as flat surfaces. We do have one surface, which is this one, all of this surface. But as you can see that this surface, it is in the pattern, it is kind of broken surface, right? It is not a straight surface, but it's still flat. Flat surface, it means just it is not a cylindrical surface. But this surface, for example, these sides, this surface here, this surface, all of these surfaces are cylindrical surfaces. You cannot choose any cylindrical surface to be a parting surface, right? So this is one flat surface, and there is another flat surface down, which is identical to the first one, right? These are the two main flat surfaces that we already have for this product. So either you choose this one or this one. For example, if you choose this one, you have to flip the product. It means it should be identical. It means that one of them is enough. I mean, like this bottom surface, the flat one, and the top surface, they are identical. It means that we just gonna have one surface as a flat surface. Another option is just to slice this pulley or this product into two pieces, into two parts, and in this case you're gonna end up with a flat surface, which it should be typically the same as we are seeing here. Assume that this is like a water mirror, as we discussed the previous meeting, and you're gonna have this flat surface. This portion is gonna work like a flat surface. So it means that it looks like we're already slicing this part or this shape into two pieces. So we're gonna end up with two identical pieces, and the parting surface, the slicing surface, will be the parting surface. In this case would be used in this case. But if you decided to choose this vertical, slicing vertically or twice, in this case we have to do casting for this pulley in the vertical position. And it is not advised as long as the length or the diameter 600 will be very long. It means that you're gonna have a flask, or the sand mold will be like a tower, standing like a tower. It is very long, and it is not advised to cast the product in this way. So there is another option. So we'd have one option, which is this one, as a parting surface. The second option is to slide the shape twice. The third option is to slide the shape in the horizontal direction, like into two pieces as a parting surface, which is gonna be the third option. So in total for this casting, we have three possibilities to choose as the parting surface. Which one is the best? In my point of view, the best one is the surface one. Why the case this surface? Because if we're already doing casting, first of all, we're gonna do this surface allow us to cast the product in the horizontal position. So we won't gonna have a very long tower shape flask or sand mold. It's gonna be a regular mold. It would be wide, no problem. But the tower thing, it will be difficult. Why? Because it will be difficult for the molten metal to go up. It is easy for the molten metal to spread in the X or Z or Y direction or going down. It's going to be much more easy for the molten metal to go down more than going up. So if in case that would have this one is vertical, so pushing the molten metal to fill the top part of the casting would be hard, and in this case we would end up with some problems and defects in the casted product. So that's why it is advised for this product, especially this one with this wide shape, to be casted in the horizontal position. This is one thing. Another thing, and this is what we can obtain by either the surface 1 or surface 3. So that's why 1 and 3 are preferred over 2. So we're gonna skip 2. Why one is preferred than three? Three, it enforces us to split the pattern into two pieces, into two parts, and you're gonna have half of the pattern would be located in the coupe and the other half would be located in the drag. And for some reason, if we didn't give a support and good support for the top part and the bottom part of the casting and the flask to be supports and hold them together, because of the pushing force, the buoyancy force of the molten metal, the coupe will be displaced and shifted from the drag, and in this case we're gonna have some defects in the final product. So it is advised in general, in case that you'd have a possibility to make the pattern as one piece and it is located in the drag, it's gonna be the best option ever. And in this case, for this product, it is advised to have it horizontal, in the horizontal position. So given this data, this discussion, we can conclude that the best option ever is the parting surface 1. This is the best option. But for this course, basically, if you choose any other option, I'm gonna accept it. But generally, if we're gonna talk about the practical use, and this is what you should do in the industry after the graduation, the best option, it should go for the surface 1. And this is what I'm gonna do for this problem. I'm gonna choose the surface 1, which is this one, as a parting surface, and you're just gonna set here like X, and X indicate that this is just a symbol that indicate that this is the parting surface. And as you can see, this parting surface is broken. It is not a straight surface. Someone gonna say, okay, I'm gonna consider the parting surface in this way, but how about this part, right? So it means that is fine to have the parting surface broken in this way. Someone gonna say, how come I can do the parting surface broken? Yes, no problem. You're gonna have the pattern as one piece. This one piece will be located in the drag, and all of these parts will be filled with the sand, right? As we agreed, all of this is just sand. But remember, there is no sand here. You're just gonna set the pattern and then set up the pattern and fill the drag. Then if you try to remove this one out of the sand, it will be removed without breaking the sand. It means that is fine so far. How about the top part? How can we fill this part with the sand? If you flip the pattern upside down, if you inverted the pattern in the upside down, and then we gonna compress, you just gonna press the pattern against the sand and fill on the top, like you're already filling the sand from the top. You're already putting sand here from the top. So there should be some sand will be filled into this space. Then if you try to remove, because now you are removing from the top part, if you try to remove down the pattern, it will be removed without breaking the sand. Then if we apply or we compress or we add the coupe to the drag together, we're gonna end up with a mold cavity will be filled in the middle here. Okay, so this is basically what we're gonna do, and this option or this parting surface will allow us to have the the pattern to be just a single piece, and this is gonna be the best option. And again, we're gonna do casting for this product in the horizontal orientation, horizontal position. Make sense? So that's it for the parting surface or the first two steps. What I'd like to mention here, that these two steps shouldn't take time from you. Directly you can come up with the shape of the pattern, the tentative design of the pattern, which it should be identical to the final product, except if you do have any opening, just add cool prints. Very simple. This is gonna give us the pattern shape directly. Then by investigating the pattern shape very quick, you can come up with the surface, with the parting surface, then look at the parting surface. That's it for the first two steps, which shouldn't take 1 minute or 2 minutes at maximum to come up with the parting surface and the shape of the pattern. Then you're gonna proceed to the one of the important steps, basically is the third step, which is the pattern design. And the pattern design, it means that your objective is just to find all the dimensions of the pattern. And we said that there are some differences between the pattern in terms of dimensions and the final product because of the machining allowance, shrinkage allowance, and draft and the draft allowances. In addition to the other differences that related to the shape in terms of the cool prints and so on. And in this step, we agreed that we're gonna form this table and we're gonna fill the dimensions in this table. to work on the machining allowance, the shrinkage allowance, the draft allowances, and the total. Then we're gonna calculate the total dimensions for the button, and it's gonna be it for the button design. But there is something that I'd like to discuss here. As you can see, there are some a little bit small triangular symbols here. What are these symbols? These symbols indicate that this surface should be machined. This surface should be machined. This surface should be machined. What does it mean, machining? As we discussed, machining and casting process, it is a post-processing of the casted product. It means that once we break the sand and we bring this product, the cast from the sand, it will be with rough surfaces and it is very dirty. So we're gonna do like very quick cleaning, trimming of the getting system. Then we have to do machining for some surfaces. In some products, it is not necessary to machine all the surfaces. Basically, we machine the important surfaces that will be in contact with other mechanical component. In case, for example, you're gonna use this one like a pulley, so this pulley will be in contact, will be used in a machine, so it will be in contact with any other mechanical elements or mechanical components. So we have to do machining and make the surfaces of this product that will be in contact with any other components or mechanical element to be very clean, very smooth surface, well machined surface. So that's why we do have some surfaces that we have to machine or to be machined, and some other surfaces that is fine if you just leave them as you got them from casting or by casting process. So the easiest way for sure is to try to machine everything, but in terms of machining itself, it is a cost. So that's why, and this basically depends on the experience. Based on the experience, you can decide which surface that should be machined, which one that shouldn't be machined. For example, in this problem, I'm helping you a little bit, and I'm providing here this symbol to indicate that these surfaces should be machined. Like this surface, which it should be this top surface, all of this surface over the top, that it basically should be like three parts, three surfaces, this surface, and this surface, and this surface. If we're gonna look to these surfaces over the product, it means that this top surface of the rim, as well as the top surface of the hub part, these surfaces should be machined. And the degree of machining, it should be 3rd degree. It means that it should be well machined, super finished somehow, because it has 3 triangular shapes that indicate that we're gonna use grade 3 of machining. The same thing for the internal hole, because there is some shaft that will be, it means that this pulley will be mounted by a shaft, and this shaft will be in direct contact with this internal surface. So this internal surface should be super cleaned and super finished. It means that we have to do machining as well for this internal hub or this internal hole with 3rd grade machining, which is deep machining kind of. But for the rim, which is the exterior, we can do like machining as well, but this machining, it would be like not deep machining, it would be like 2nd grade middle machining for this intermediate machining for this rim, which it should be this cylindrical surface. Also, it should be machined. But any other surfaces, there is no need to waste time and cost to machine them. Like for example, this surface, there is no machining for this surface. There is no machining here. There is no machining to this internal surfaces, right? So all of these surfaces, it is not required to do machining for the other surfaces. Only 3 surfaces that we have to do machining for, which are the top surface, even the bottom surface. We didn't include here a symbol for the bottom surface, but if there is something here, we have to do machining as well. Also, we have to do machining for the internal hole and the external surface, cylindrical surface of the rim. Make sense? Nothing else should be machined. If we did machining, it means that we're already wasting time and cost for nothing. Make sense? So in case that these symbols here will be provided, this indicates that there should be machining should be done. And this symbol, it would be any symbol. It shouldn't be just triangular shape. It would be arrows, for example, and we could add include some arrows here that indicate that there should be machining over this surface. Whatever it is, it's just any symbol that agreed among the engineers and the manufacturers in the manufacturer or the company, that we agreed that to include this symbol to indicate machining. So in this way, we can apply these machining as already given here. So what does it mean this for this problem? This means that while you calculate the machining allowances, you won't, or we will not add machining to all the surfaces. We're just gonna add machining allowances just for the surface that should be machined. But how about the other machining? We will not add any machining allowances to the other surfaces that shouldn't be machined. Very simple, okay? So how we can do it? In the beginning, I'm gonna work with this problem. Like I'm going to assume that I'm going to machine all the surfaces. So in the beginning, I'm gonna solve and come up with the dimensions of the button, assuming that I'm going to machine all the surfaces first. This is, I'm just gonna do it because I would like to give you a practice in case that we have to machine all the surfaces. All right. Then I'm gonna show you how you can skip the surfaces with no machining and just add the machining allowance to the one that with the machining symbols as given here. So in the beginning, let us assume that we are going to machine all the surfaces as a practice. This is like a practice. This example, it is just a practice. So let us consider the case that we are going for now. We are going to machine all the surfaces. So what was the first thing that we have to do for the pattern design? First of all, you have to fill into these dimensions table. All the dimensions that already given here, you should plug them into, drop them into this table. So we do have here the 600 diameter, the 400 diameter, and the 50 diameter, and the 250 diameter, in addition to 300 height and the 80 height, right? Or thickness of the web. So we do have these dimensions, which are the, I'm gonna fill these dimensions here. We do have the phi 600. This indicates the external diameter, and we do have the phi 400, which indicate the internal surface of the rim, and we do have the external surface of the hub, which is 250. In addition to the hole of the hub, this should be the hole of the hub. In addition to this should be the hole of the hub, and we do have here the height, which is 300, in addition to the 80, which is the web thickness. These are the given dimensions here, right? Then we have to repeat here the other dimension that will be affected by the draft that we have to add to the pattern. And we said that the draft or the taper allowance, we are adding it to the pattern to make it easy for us to remove the pattern from the sand during the sand molding process. And the draft, it means that any vertical surface that is normal or perpendicular to the parting surface, it should be oriented and tapered with 1 to 3 degrees to make it easy for the pattern to be removed from the sand. Make sense? So how many vertical surfaces do we have? This is the orientation of the pattern, how we are going to cut the pattern, or this is the orientation of the pattern that where it should be located in the sand. It should be located horizontal as given here, and this should be the parting surface, right? So how many vertical surfaces? Would have so many. Would have this one is a vertical surface, would have this one vertical surface, this one is vertical surface, and so on. All of these are vertical surfaces. The question is, should I do taper or apply taper allowance to all of these vertical surfaces? Practically, we are not adding taper allowances to all the surfaces. We are adding taper allowances especially to the surface that we are going to machine. If there is surface that you are going to machine, there is no need to add a taper allowance to this one, especially in case that the height of the surface is short. Like here, the height it is short in comparison to the 300. The same thing, this surface is short, this surface is short, this surface is short, this one is short. But the longest two heights are, or vertical surfaces are these two surfaces, which you should understand that these two lines belong to the same cylindrical surface. It means that we are talking here about only one surface, which is this cylindrical surface that belongs to this line and this line. Make sense? So what does it mean? I'm gonna say that I'm gonna add one taper allowance over this surface, over this line. Instead of having this line vertical, it will be inclined. It will be inclined with an angle here. This angle will be a very small angle. Let us assume that we're gonna use like 1 degree or 2 degree. It's up to you. The same thing here. I'm gonna apply here a taper allowance on the other side. a taper allowance over the other side, and this taper allowance will be it should be the same. It should be the same because here we are talking about the same cylindrical surface. It means that this cylindrical surface of the product, it will not be vertical. Instead, it will be like have some taper thing here. It will be tapered somehow from both sides. It means like it is already like have a conical shape open up, right? So if we apply this pattern to this, if we apply this taper or draft allowance to the pattern, which one of all of these dimensions that would be affected by the pattern or the taper? So for example, it's going to be the 600. The 600 will have two dimensions. The 600, it should refer. 600, this is the dimension that defines the distance between this line and this line, right? Now these two lines, they are not vertical anymore, and instead they already inclined, they already tapered somehow with an angle 1 degree. It means that the 600, it should have two values, one value between these 2 points, and there should be another value between these top points here, right, of the same surface. It means that we're gonna have 600 plus some taper allowances that should be added here. So that's why the dimension that it will be affected by the taper allowance will be the 600. So that's why, and only the 600, none of the other dimension would be affected by the taper allowance. It means that for this case, the 400, for example, it will not be affected. The 400 is the distance between this line and this line. So there is no taper here. We agreed that we will not apply any taper allowance to these short surfaces. The 250, it is the distance between this surface and this surface, or this surface and this surface. It is still the same surface, and we will not apply any taper allowance. It means that the 250 will not be affected by the taper allowances. The only dimension that will be affected is the 600 dimension. So that's why in the table down here, I'm going to repeat this one, 600 phi, and I'm gonna add here PS standing for the parting surface, because this is the one that will be affected by the draft that should be added to the parting, to the pattern, to allow for the easy removal of the pattern from the from its parting surface. Make sense? Then our objective is just to fill into this table for the machining allowances. The machining allowances, this table is already provided, and we're gonna use it. We said that this table, it is a common table that you use for the machining allowance for steel. For any other material, there should be another table. For aluminum, cast iron, there are different tables. Anyway, the table will be provided, will be given to you. And the objective is just to use it to fill into the machining allowances. How it works? You should distinguish between the top, the bottom, and the side surfaces. As given for this product here, we mentioned that any horizontal dimension, it connects two sides. Like one side from the right side, and there is another right side, since we already have cylindrical shape with one projected view, which is the front view in this case. So it means that the 400, the 600, it connects this side surface to this side surface. The 400 also connects this side surface to this side surface. The 250 connects side to side. But any vertical dimension, it has two possibilities. It has two or three possibilities. The vertical dimension, it would connect top surface to bottom surface, or top surface to another top surface, or top surface to bottom surface. So there are three options that we have to investigate for all the dimension that already filled in the table, and this is what we're gonna do. Make sense? So let us start here with the first dimension, with the 600. So what you're gonna do, you're just gonna go to the table, ask the dimension that I'm gonna work on is 600. Then you're gonna go to this column, and then you're gonna ask, the first step, as we mentioned, that we have to identify the maximum dimension of the whole casted product. The maximum dimension should be the maximum width and the maximum height. The maximum width of this one will be 600. The maximum height, it is 300. So the maximum dimension for this product will be 600 millimeter as a maximum dimension. So using this 600 millimeter, I'm gonna go to this table. Ask yourself, is the 600 less than 120 millimeter? No. Is it between 121 up to 260? No. Is it between 261 up to 500? No. 501 up to 800? Yes. Then what you have to do, you have to mark over this row all the problem till you finish this table. Any dimension, any number, it should be collected from this row. Make sense? Then what you're gonna do, you're just gonna investigate one by one dimension by one dimension. So starting with the 600, then you're gonna ask yourself, is the 600 less than 120 millimeter? No. Is it between 121 to 260? No. Is it between 261 up to 500? No. So the 600 is bigger. So in this case, you're gonna consider, because this is the maximum one. Because this table, people prepare this table based on some empirical formula, and basically in case that you have a dimension that is bigger than the maximum dimension here, you're gonna consider it within this column. It means that you can consider that this is 500 or above. So it means that the 600 should be located within these three columns, and you do have three possibilities here, either to pick these two numbers, depending on what? Depending on the machining allowances or the degree of machining that we have to apply to the surfaces. In the beginning, let us assume that we're gonna do deep machining with third grade machining to all the surfaces, as we agree. So it means that we're gonna pick one of these two numbers or both for the dimension 600, depending on what? Depending whatever the 600 connects top surface or bottom surface or the side surface. In case that it connects top surface, the top surface is gonna take 10 millimeter machining allowance, but the bottom or the side surface is gonna take the 7 millimeter machining allowance. So going to the drawing here, to the shape, to the final product or the pattern, the 600, it connects two surfaces, which are this surface and this surface. These two surfaces are two sides. Each one, it should take 7 millimeter machining allowance based on this table. These are the two numbers. The side takes 7 millimeter. It means that we should have this surface, it should be bigger. It means that we have to add here 7 millimeter, and the 7 millimeter to be added, it should be added outside the metal. It should be added in the empty space. There is metal side here, so it should be added on the left. There is metal, it should be added to the right. So if we added 7 millimeter here, it will increase the 600. The 600, it won't gonna start from this point, and instead it will start from another point, expanded. It means that we are going, this 7 will increase, will add other dimension to the 600. How about the other surface? We're gonna add here 7 millimeter as machining allowance to the other surface. So this other machining allowance to the other surface also will increase the dimension 600 by 7 millimeter. So in total, the 600 dimension will be increased by both the machining allowances to its both surfaces, the 7. So we're gonna have plus 7 to both surfaces. Make sense? How about the 400? Do the same. The 400 here connects two surfaces, which are this surface and this surface. But you should understand that this surface is typically the same like this one, is typically the same like this one, is typically the same like this one. All of these are cylindrical surfaces. So the 400, it connects all of these four lines together, which should be the same surface at the end. So the 400, it connects side surface to another side surface. Agree? So side to side, if we're gonna go down here to the table, go to the 400. The 400, is it less than 120? No. It is 120 to 260 up. It is 261 up to 400. Yes. And we're gonna do machining to all surfaces using third grade. So we're gonna have 10 millimeter to the top surface, 7 millimeter to the side or bottom surface. The 400, as we agree, it is side. So we're gonna add 7 millimeter to the surface, and we're gonna build another 7 millimeter over this surface. Why the 7 millimeter is added here to the right, there on to the left? Because the right side here is metal, so we have to add the 7 millimeter in the space, in the empty area, and we have another empty area here because there is metal on this side. So how about this 7 millimeter? Is it going to increase or decrease the 400? This 7 millimeter will decrease. it is gonna cut something, remove something from the 400 millimeter from this side. The same thing applies to this 7 millimeter. For example, this 7, the actual dimension will be from this surface to this surface. It means that the 400 has been decreased by 7 from the right and another 7 from the left. So it means that these 7 and 7 from the both sides should be subtracted from the 400 millimeter. Make sense? How about the 250 millimeter? The 250 millimeter, which is this one, it connects also two surfaces, which are this surface and this surface, which it should be physically the same cylindrical surface, which is the external of the hub, and we do have this is the same surface here, right? So this external of the hub with a diameter of 250 millimeter, these two surfaces are two sides. So going back to the table, the 250, you're gonna find it is located within this range, 120 up to 260, and we are working over deep cleaning or deep machining. So we do have two numbers here, the 8 for the top surface, the 6 for the side or the bottom surface. We agreed that the 250 up, it is a side to side. Connect two side surfaces. It means that each surface is gonna take 6 millimeter as a machining allowance. So if we decided to build 6 millimeter machining, it should be built on the right here. This is the empty area. There is metal on this side, and there is another 6 millimeter on the other side. So this 6 millimeter from this side, definitely it will increase the 250, and the other 6 millimeter will increase as well the 250. So we're gonna have in front of the 250, we're gonna add plus 6 plus 6. It means that we're gonna add to both sides 6 millimeter as machining allowance. Make sense? How about the 50 millimeter, which it should be the hole? The hole here, it connects two surfaces. This hole, which it should be the hole in the final product, right? This hole in the final product, it connects two surfaces, which are this surface and this surface, right? This surface is a side surface and this one is a side. We said that any horizontal dimension connect two sides. So this is a side surface, this is another side surface. So if we're gonna go down here to the table, is the 50 less than 120? Yes. So it means that we are located within these three columns, and since we are using deep machining, which is third grade, it means that we do have 7 millimeter for the top surface, 5 millimeter for the side or the bottom. We agreed that the 50 connects side to side. So each side is gonna take 5 millimeter as machining allowance. So if we try to add here 5 millimeter, the 5 millimeter it will be added inside the hole, and the other 5 millimeter it will be added inside the hole. Why inside, not outside? Because there is metal here, there is metal on the other side, so it should be included inside the hole. These two machining allowances will decrease the hole. The hole will be decreasing. The diameter of the hole was 50, now the hole becomes very smaller diameter. It means that both will decrease the 50 dimension. So we're gonna increase the 50 millimeter with two machining allowances that we got here by 5 millimeter for these side surfaces for the 50. So we're gonna have here -5 for this hole, -5 for this hole from the other side. Make sense? How about the 300? Do the same. If we're gonna go to the drawing here, the 300, it connects this 300. It connects two surfaces, this top surface and this bottom surface. How did I know that this 300 connect these two surfaces? Nothing else. Simply, it is very simple. If you just try to draw a line that is perpendicular, draw a line. This is the 300, and draw a line that is perpendicular to the dimension line. This is the dimension line. Draw a line that from the end, perpendicular to the dimension line. Draw another line from the end that is perpendicular to the dimension line. This is gonna give us the two surfaces that should be connected or related together through the 300. So this 300 defines the distance between these two surfaces. One of them is a top surface and the other one is a bottom surface. We discussed in the previous videos that a top surface is the one that if you try to look to the shape while it is oriented in the casting position, if you try to look at it and you're gonna see the surface, this surface will be a top surface. But if you cannot see the surface, it will be counted as a bottom surface. So again, the 300 connects this surface to this surface. If you try to look to the shape from the top, are you gonna see this surface or not? Yes, you're gonna see. And you should keep in mind that this surface, it should be all the way till the end. If you try to look at it from the top, you're gonna see it. But can you see this surface? No, I won't gonna see this surface. So this surface will be counted as a bottom surface, while this one, it will be counted as a top surface. So we're gonna conclude that the 300 millimeter dimension, it connects two surfaces. One of them is top surface, the second one is a bottom surface. And then we're gonna go to the table down here. The 300, is it less than 120 up? It is 120 to 260 up. It is between 261 to 500. And we are using deep machining, third grade. So we do have here 10 for the 10 for the top surfaces and 7 millimeter for the side or the bottom surface. We agreed that the 300 connects top surface and bottom surface. The top is gonna take 7, 10 millimeter. The bottom surface is gonna take 7 millimeter. So what does it mean? It means that for the 300, I'm going to build over the surface. The surface, it should be thicker or something built over the surface. While, for example, if you try to do machining, it means that we have to remove this part. When we try to remove this part, when it will be removed, we're gonna end up with the cleaner surface of the final product. So it means that this surface, it should something build up over this surface here. This something, it should be 10 millimeter. This 10 millimeter definitely will increase the 300. The 300, it will not be from here, it will start from above with 10 millimeters, so it's gonna be 300 plus 10. How about the bottom surface? It's gonna be the same. We're gonna build over this surface. While we try to remove this part, it will be removed. So if we try to build over this surface, we're gonna build 7 millimeter because it is a bottom surface according to the table. This 7 millimeter will increase as well the 300 dimension. So what does it mean? The 10 and the 7 both are going to increase the 300. So we're gonna have 10 millimeter plus the 7 millimeter, both are going to increase the dimension 300. Make sense? Keep going. How about the 80? The 80, which it should be this dimension, this web thickness. This 80, it connects two surfaces. One surface is this one, and the second surface is this one. How did I know that this area connects these surfaces? So these two surfaces, it is very simple. I can draw the dimension line of the 80 in this way. Agree? It refers to the same thickness, right? But it is already drawn in this way. So this dimension, as usually or normally should be drawn or represented. This, if you try to draw a line normal or perpendicular to the dimension line and another line from the end perpendicular to the dimension line, this is gonna give us these two surfaces. So these are the two surfaces that already connected or related by the 80 dimension, which should be the same surfaces here, which should be the web surface, this one, and the other similar surface that is not shown from this view for this three-dimensional representation of the product. Make sense? So what does it mean? It means that we do have the area connects two surfaces. This surface, is it bottom surface, top surface, or side surface? It is a top surface. Why? Because if you try to look at it from the top view, you're gonna see this surface. So this surface, it should be top surface. But how about the other surface, which is this one? If you try to look to the shape from the top, are you going to see the surface? No, this should be the bottom surface. So it means that the area connects a top surface to another bottom surface. So going back to the table, the area, it is less than 120 millimeter, and we are doing deep machining, third grade. So we have two numbers, 7 for the top surface and 5 millimeter for the bottom or the side surface. We agreed that the area connects top to bottom. So we're gonna have 7 millimeter to the top surface, 5 millimeter to the bottom surface. Going back again to the area, we're gonna build 7 millimeter over the top surface. This 7 millimeter will increase the area dimension, and we're gonna build another 5 millimeter over the bottom surface. This other 5 millimeter as well will increase the 80 millimeter. So both 5 and 7 both will increase the 80 millimeter. It means that in front or next the area, we're gonna add plus 7 as machining to the top surface, plus 5 as machining to the bottom surface. Make sense? So we finish all the dimension. We still have only the dimension that has been repeated, which is the 600. So what we're gonna do simply, we're just gonna repeat these numbers, which are plus 7, plus 7. Just get on or copy these numbers again next to the 600 parting surface or repeated dimension. Make sense? So this is simply for the machining allowance and allowances. And again, I assumed that I'm going to machine all the surfaces. I didn't care of this machining symbol that were given. So, but basically in this problem, these machining symbols were given, so we have to stick to them. We have to apply them or consider them. It means that we are not required to machine all the surfaces. So what does it mean? It means that there are some of the surfaces that should be skipped. And this is what I'm going to do next here for this table. So I'm gonna repeat again, but this time I'm gonna skip the machining allowances or repeating all the machining allowances in this way. All right, so we're gonna copy again all the dimension. I'm just gonna copy this one. So I've copied these dimensions one more time, and let us repeat the thing that we did, but now we're gonna skip some surfaces and we're gonna skip some machining allowances. So let us start with the 600. So if we're gonna go to the shape, the 600 in this given product, the 600, it connects two surfaces or two lines as given here, which are, they should be, the 600 connect this line to this line. And as you can see, the surface has a machining allowance on this side, but there is no machining allowance here. So what does it mean? It means that I should add a machining allowance to this surface because I'm going to do machining for this one. But it means from the first look, we're gonna say that there is no machining to this surface. But actually, there is a machining to the other surface as well. Why? Because this machining, it doesn't make sense that you machine half of a cylindrical surface and leave the other half without machining. Because the 600 here, it connects, it refers to a cylindrical surface. And for cylindrical surfaces, that is fine to add the machining allowance on just one side. Intuitively, since it is one surface, it means that all the cylindrical surface should be machined. So this symbol, since it is already written or represented over one line, intuitively it should be as well over the other line. But there is no need to redraw again the same symbol over the other line, because intuitively the 600 refers to a cylindrical surface and all the surface should be machined. So you should understand that this symbol, it should be repeated here. It means that we are going to add machining to both sides, not just one side, right? And the degree of the machining over this surface is second grade. It is not a third grade. So for the 600, it connects a side surface to another side surface, as we discussed before, but the grade of the machining, it is second grade. So going back to the table, the 600, we're still gonna use the same column, the same row, because this basically depends on the maximum dimension with the 600 that we located in the beginning. So the 600, it will be located here. It is between 261 up to 50 and above. So it is higher than 500. It means that we're gonna use these three columns, and we are working as second grade or grade 2 for the machining. And the 600 connects side surface to another side surface, so both surfaces gonna take 6mm machining. So what does it mean? It means that I'm going to add here, I'm gonna build 6mm to this surface, and there should be another 6mm over this surface. This 6mm will increase the 600, and this one also will increase the 600, as we discussed before. So what does it mean? In front of the 600, I'm going to add here, for this case, plus 6 plus 6. Here, I'm considering the symbol that were given to us for the machining allowances over these dimensions. Then the next dimension is the 400. The 400, it connects two side surfaces, this one and this one, right? But and you should keep in mind that this surface is typically the same like this one and this one, because the 400, I can write the 400 here. I'm still talking about the same dimension, right? So do you see any machining symbols already located or identified to these surfaces? No, there is no machining surfaces here. So what does it mean? It means that we are not required to do machining to to these surfaces, it means that there is no machining allowances will be added to the 400 millimeter dimension. It means that next to the 400 millimeter in the table, you just gonna mark there is no machining. There is no machining will be added to the 400 millimeter dimension. It means that there is no need to go to the table. Make sense? What next is the 250? Do the same. If we're gonna go to the shape for the 250, 250 connects these two lines, this line to this line, which is still the same cylindrical surface, which it should be the cylindrical surface of the hub. Make sense? So this surface, which should be the same surface, do you see any machining allowances or machining symbols over these surfaces? No. So there is no machining that should be done for these surfaces, cylindrical surface that belong to the 250. It means there is no machining allowances would be added to the 250 millimeter. So going down here to the table, we're gonna say that there is no machining. This mark indicates there is no machining for the 250. How about the hole? The hole, it has a machining symbol, right? And if we're gonna go to the shape, there is a machining symbol here of third grade machining, deep machining for the internal hole. And as you can see that the machining symbol has been located over one side. How about the other side? It should be the same because the hole, it is a cylindrical surface. So the machining surface, the machining symbol, the machining surface over one side of a cylindrical surface indicate the overall surface. It means that both sides or the cylindrical surface, the overall cylindrical surface should be machined. As we discussed before, the 50 millimeter, the hole connects two sides, one side and one side, and it is third grade. So going down to the table, it means that there is machining, so we have to go to the machining table. Is it less than the 50, less than 120? Yes. And we're gonna do deep machining with third grade, and it connects side to side. The side takes 5 millimeter side. So if we're gonna go up to the shape, the 5 millimeter, the 50 millimeter, we're gonna add here 5 millimeter over this surface and another 5 millimeter over this surface. These two 5 millimeter will make the diameter decrease of the hole. It means that this 5 millimeter will subtract it from the 50 and this one will be subtracted as well. So both will be negative machining allowances that should be added next to the 50 hole. So we're gonna have -5 and -5. How about the 300 dimension? The 300 dimension here, it connects two surfaces, which are this surface as a top surface as we discussed and this bottom surface, right? But as you can see, these surfaces are not cylindrical surfaces. So what does it mean? It means that this surface is different than this one. So the 300 here connects two different surfaces, but the 600 was connecting to the same surface. We still, for the 600, it connects the same one surface, not two surfaces. But the 300 connects two different surfaces. So what does it mean? It means that it's fine to add machining to this one, but we can machine one surface and there is no need to machine the other surface as indicated here. This surface is the only one that has machining symbol, but this one has no machining symbol. So what does it mean? It means that we are going to add a machining allowance to one side, to one surface, and we won't gonna add machining allowance to the other surface. This surface is a top surface. It means that we're gonna add a machining allowance of a top surface and it should be third grade. So going down to the table, here, the 300 is going to be within this range, 261 to 500, and it is deep cleaning or deep machining. So 10 millimeter to the top, 7 millimeter to the bottom surface. So we're going to go again to the dimension. The 300, it connects top surface that should take 10 millimeter and bottom surface that should take 7 millimeter, but we're gonna skip this 7 millimeter. We won't gonna do machining to the bottom surface. So what does it mean? It means that we're just gonna do machining to the top surface only. We're gonna build 10 millimeter here, which should increase the 300. So what does it mean? Next to the table, next to the 300 in the table, we're just gonna add plus 10 only. There is no plus 7. Why? Because we just gonna machine only one surface. This is gonna be plus 10. How about the 80 millimeter dimension? The 80 millimeter, it connects two surfaces. As we agreed, it should be this surface and this surface, which it should be this surface and this surface. or in this drawing, it should be these four surfaces, this one and this one. This is one surface, this is a different one. This is one surface, this is a different one. But you should understand that this surface is the same like this one. But this one and this one is similar to this one. But these two or these two are different. Anyway, none of these four lines has any machining symbols, right? This indicates that we won't gonna add any machining allowances to the array, so there is no machining allowances to the array. Just add one big dash in front of the or next to the array. How about the 600? Just copy the thing that you had here. We already added +6 and +6. How about if we didn't add any? We put dash, you just gonna add dash here. Make sense? So this is for the machining allowance. This shouldn't take time from you. I'm explaining to you. I solved twice. So if you try to do it and practice well, this procedure or this step will not take time from you. The next thing is to fill into the shrinkage allowance. He didn't mention anything in the top of the problem for the machining for the shrinkage allowance. So it's up to you. You can consider any value as a machining allowance, but we advise that for steel, the general value for the machining allowance, it is 2%, it's just 1%. So what does it mean? It means that I'm going to add here a machining allowance for this dimension by 2%. Let us assume that we're gonna use 2% as machining allowance. So how we can add the machining allowance? Your objective is just to add the numbers. It is 600 plus 12. This gives 612 times 2/100 equals, and just put the number here, which is gonna be 12.24. And then repeat for the rest. It's gonna be 400 plus 0. So it's gonna be 400 times 2/100 equals 12. I'm sorry, this is gonna give us 8 millimeter. And then 250 plus 0, this is gonna give us 250 times 2/100 equals, and this is gonna give us 5 millimeter. And for the 50, we're gonna have 50 negative 10. So this should be 40 times 2/100 equals the 1.6. And for the 300, it's gonna be 310 times 2/100. This is gonna give us the 6.2. Just do the calculation. And then the 80 plus 0, this is gonna be 80 times 2/100. This is gonna give us the 1.6. Make sense? How come that this should be the same number? Okay, it seemed that I did something wrong in the calculation, because this should be like 80, so this should be doubled. So let me double check these two numbers again. So the 50, it should be 4 times 2.40 times 0.2. This gives us 0.8. This value, it should be 0.8. Make sense? As for the shrinkage allowance. All right. So we got this one. How about this machining allowance? It should be the same. It should be the 12.24 that we already got before for the same dimension. Then we are going to add the draft allowances. The draft allowance, we said that the only dimension that would be affected by the draft allowance is the 600 millimeter, right? So going up here to the 600 dimension, and we agreed that we are going to add a taper allowance here. So let us assume that this dimension is x1. It means that this extra portion will be x1, and the taper will add here another x2. As you can see, the x, we said that either x1 or x2, it should be the height times the tangent of this angle. The height here, it is 300, so it should be 300 times the tangent of the angle, which is 1 degree. How about x2? It should be the same height, right? Which is 300 times the tangent of 1 degree. This is 1 degree. This is the angle that we assume that we're gonna add as a taper allowance. You have a range between 1 to 3 degrees. It's up to you. Pick either value, either 1 degree or 2 degree or 3 degrees. So if it means that this indicates that x1, the taper allowance that we're gonna add to the 600 millimeter, both are equal from both sides. And as you can see, this x1 will increase the 600. The same thing here, this x2 will increase as well the 600. We agreed that that is fine if we skip these vertical short surfaces because they are short in comparison to the other one. So the big deal is already going for the draft allowance for the big or the largest vertical surface, which is this vertical surface and this one, which will affect these draft allowance, will affect the 600. That's why we repeated it in the table down there. So adding x1 and x2 to the 600, it means that we're gonna add 2 times 300 times 10, 1 degree to the 600 next to it. So in the draft allowance here, we won't gonna add any draft allowances to all of these dimensions. The only one that will be affected is the one with the part surface. It means that that's why we do have 2 different values for the 600, right? 2 different values. One value that is away from the parting surface, which is this one, because when we taper this surface, it will be taper shape. Any taper shape should have 2 dimensions, 2 diameter. One small diameter, which is away from the surface, and there is another diameter that is already at the parting surface. So that's why we have to distinguish between these 2 surfaces even in the table down here. Like we're gonna have 1 600 without PS, it means that this is the 600 away from the parting surface, and there is a 600 with a PS, which stands for the parting surface. It means that this is the 600 over the parting surface. This is the one that is going to increase. One should be bigger than the other. So that's why this one has no draft allowance, but this one we're gonna add draft allowance of 2 times 300, the tangent of 1 degrees. Make sense? So if we did the calculations, your objective then is just to sum all of these dimensions to fill into this column, and this what give the dimensions of the pattern. So what I've did here, I just added all these dimensions, added these rows together. This is gonna give us the exact dimension of the pattern that we have to make, and this pattern should be made of wood or any other simple manufactured material like wood, for example. This is the common thing. And if we decided to these are the dimensions that we have to use for making the pattern, and instead of the exact dimension of the product that already given here. So these are the dimensions of the product, and the dimension that we identified or we got in the table. These are the corresponding dimension but for the pattern. Make sense? So this is for the third step, that basically it takes time in comparison to the other steps. But if you try to practice this one, it's gonna be very quick, and you can directly distinguish between top and side surfaces, so you can come up with this table very quick. So I explained through this step 2 cases. In case that we are going to machine all the surfaces, then I explained according to the given information or the given problem, we are not required to machine all the surfaces, so that's why I skipped some surfaces here in the machining allowances. But the shrinkage allowance definitely should be added to all the dimensions. The same thing for the drafted allowance, it will affect some dimensions and it will not affect the others, and this is what we done for the third step. So now let us move to step 4, which is the core design. In this step, basically, as we discussed, the objective is just to come up with the dimensions of the core that should be used for making the internal hole. In case that the problem or the product that we are interested for to make it by casting, in case that this product has no hole, in this case there is no core. It means that you're gonna skip step 4. But here, since we do have internal opening with 50 millimeter diameter, this is like a circular opening or cylindrical hole. So the core should be identical in terms of the shape, but with some extra core prints as we discussed. So the objective is just to come up with the dimensions of the core in terms of diameter, in terms of length, in addition to the length of the core prints. And you should understand that we already got the diameter and the length of the core. How? Because anything, as we mentioned even in the previous videos, once we finish this table, any dimension that we gonna get from the problem itself, from the product, final product, it should be converted into its new dimension. Because from now on, we're gonna work on the dimensions, or we're gonna use the dimension of the pattern that we got from this table. So what does it mean? It means that, for example, if we're gonna jump up here to the final product itself, if I ask you what is the diameter and the length of the core that should be used here, so you're gonna tell me that it should have a diameter of 50 millimeter and it should have a length of 300 millimeter. But you have to translate, you have to find or convert this 50 and 300 to its new value that we got from the table down there, right? So like we do have here for this core, it should be with 50 millimeter diameter and 300 millimeter diameter. So what we're gonna do, we're gonna go to this table here that we finished, and we do have 50. The 50 becomes the 40.8, and the 300 becomes the 316.2. So this should be the length, this should be the diameter and the length of the core that we have to use. So in this case, and you should understand that the core is already oriented vertical in the drawing. So we do have the core that is already oriented vertical. So this should be the core in this case, and there should be some core prints, right? And it is oriented vertical. As we discussed before, in case that we do have a vertical core, this dimension, it should be h1, and this h1 we're gonna get it from the table, and the one on the top, the core print on the top should be 0.6, which is 60% of h1. These like fixed relations. And we do have here the length of the core, which should be the 300. The 300 we got it in the table, 316.2, and the diameter of the core we got it by 14.8. So we're gonna use these two numbers to come up with a value of each one from the table. As we discussed, you're gonna go to the core diameter. The core diameter, it is 40.8. So is it up to 25? Nope. It is 26 to 50. Yes. So it should be one of these numbers that located over this row, right? Some of these numbers. Then, how much is the length? The core length, it is 316.2. So it should be located within this range. This range, 301 to 500. And we do have two numbers here. H1, it should be 70 millimeter, while I, it should be 60. I'm gonna skip I don't need I, but I need the H value. The H1, because why? Because the core is already oriented vertical in this case. So from the table, we already got H1 equals 70 millimeter. So in total, the core length, the length of the core total, should be like the total core length. It should be the 316.2 plus the 70 plus the 0.6 times 70. This is gonna give us the total core length in millimeters. Make sense? Even we can do the calculation, or even if you just represented the core in this way, that's enough for me. So if we calculated this value, this is gonna give us the 428.2 millimeter at the core length. Make sense? And that's it for step four. Then we're gonna move to the next step, which will take time somehow, which is the calculation of the gross weight. And we said that the gross weight, it required the calculation of the volume of the casting. What is the casting or the mold cavity? It should be the volume of the cavity that already filling inside that will be formed, or the cavity that will be formed inside the sand. And these cavities will include the mold cavity in addition to the cavities for the gating system and the riser as well. And we said that the cavities for the gating system and the riser, these consume like 30% of the mold cavity itself. So what does it mean? It means that to come up with the volume or the gross weight of the molten metal, we're gonna calculate the volume of the mold cavity. Then we're gonna add. Then after that, we are going to then we are going to add the 30% to this volume to end up with the total volume. Then if we multiply times the density, we're gonna come up with the weight in terms of kilograms as mass, or the mass of the gross mass. And this is the objective of the step 4. So in step 4, moving forward for step 5, there should be step 5. Here is just to calculate the gross weight or gross mass of the casting. So how are we gonna calculate it? It's gonna be very simple. First of all, you have to calculate the volume of this shape, the volume of this product here. So what I'm gonna do, I'm gonna copy this product. So now we have a copy of the final product dimensions. This should be the final product, and all of these dimensions, these are their corresponding values, new values that we have to use for the calculation of the volume. But if I ask you to calculate the volume of this shape, so you have to break it down into some simple shape, then you're gonna calculate the volume of each one of these simple shape, then you're gonna add all of these volumes together to end up with the total volume. And this is what we're gonna do. So if we decided to break it down, you should somehow understand and visualize what is this shape. So basically we can break it down into a rim. We can consider like this piece, this part, like it is like a ring, like volume 1. This is like a single part. You should understand this point, right? So this is gonna be like volume 1. Then we're gonna have the web. The web is gonna be, or the hub in the middle with some internal hole of diameter 50. This is gonna be like volume 2. Then you're gonna have the volume 3, which it should be the web. This is gonna be volume 3, which is this one. So if I use different color, we're gonna say that this is like volume 3, and we do have here, this one is volume 1. So okay, let me, because we need the numbers, so I'm gonna use here like this is volume 3, and we do have the green thing. This should be like volume 1, which is the ring. In addition, we do have volume 2, which is the hub in the middle. Then your objective is just to calculate these volumes using the dimension that we have. So in the beginning, you can, as we break it down into some simple shapes. So for example, as for volume 1, it should be like a ring. As I mentioned, this is like a ring in this way. So the ring basically should have a height, and the height here it is 300 millimeter height. In addition, it has two diameters, one external diameter at 600 millimeter, and the internal diameter is already given by 400 millimeter. So if I ask you this, it should be like volume 1. Now let us draw again the volume 2. Volume 2, it should be the hub, which is gonna be like a cylindrical shape with some internal cylindrical hole as well. It's gonna be in this way. The height of this hub, it should be 300 as well, right? The total height is 300. The diameter, it has two diameters. The external diameter is already given by 250 diameter, and while the internal hole, it is already given by 50 diameter. Make sense? And this should be like volume 2. For volume 3, it should be also like a ring. It's gonna be like, there is an external diameter and there is another internal diameter, and there is like a little bit small thickness. The thickness of the web here is already given by 80, and the external diameter is the 400, while the internal diameter of the web, it should be the 200 millimeter diameter. So we're gonna have here, this is gonna be it. So the thickness, it's going to be the 80 thickness, while the external diameter, it should be the 400 diameter, while the internal diameter is the 250 diameter. Make sense? Then your objective is just to calculate each one of these volumes. So if I ask you how much is the volume V1 for this shape, so it is a cylindrical shape. So the diameter or the volume of a cylindrical shape, it should equal to the area of the base times the height, which is 300, right? This area of the base, it is the area of external area, and there is another subtracted area of a diameter. It has like two diameter, internal and external diameter. So it is commonly known that the area of these two circles, the area between them, between these two circles, like you do have a cylinder with an opening, so it's gonna be pi over 4, the external diameter square, which is d square, 600 square, plus negative the internal diameter square, and this should be multiplied times the height, right? Very simple. But this one gonna be the volume that we need. This is the volume of the product, right? So, but the volume of the casting that we basically need, so we can give this one like V1 bar, and the V1 that we really need is you have to translate, you have to come up with the equivalent values, the new values of these numbers or this dimension from this table. As we mentioned, once we finish any number, any dimension that we're gonna get from the final product, it should be converted into its equivalent value. So here, for example, like the 600, and this is what I'm gonna do. When we are going to calculate, then we have to calculate, for example, V1 of the casting. V1 of the casting, it will be pi over 4. The 600 here, it has two values in the table, this value and this value. So it's up to you. In some cases, that is fine. For example, if you pick the maximum value, or you just pick the average between these two values, and this is going to be much more accurate if you take the average, because this 600, it has two values because it has like a trapezoidal shape. So for this, that's why it has like two diameter, so it's gonna have like a conical shape. I won't gonna ask you to accurately calculate the conical, because this is gonna be like a conical shape with a cut top. The top part of the conical shape will be cut. I won't gonna ask you to do accurate calculation to come up with the exact shape or the exact volume of this conical shape. Just give an approximate calculation, and this is even what we are doing practically. All right, so what I'm gonna do, you can take the average of these two numbers, because the 600 has two values. It means that this surface will be tapered surface, conical shape. It means that this ring, it won't gonna be cylindrical, it would be have some conical thing, right? So I'm gonna calculate I'm gonna pick the average of this diameter, just a symbol to make the calculation more simple, and it's gonna be acceptable. The difference, even if you try to do it accurately for the conical shape, you're gonna end up nearly with almost the same result or the same value, which is, it's gonna be accepted, as I said. So that's fine to have the average between these two diameters. So I'm gonna pick here the average of the 600 from the table. It has two values. I'm gonna calculate the average. So it's gonna be 624.24 plus the other value, which is 634.7 divided by 2 square. This is gonna give us the first 600 negative. Remember, there should be like a square bracket here. The 400 in the table became 408 square times, this should be multiplied times the 300 in the table became 316.2. Then you're gonna multiply, because all of these dimensions are given in millimeter, and we are interested to come up with the value of the volume in terms of centimeter. So we're gonna multiply times, it should be 10 negative 3, because we are converting from millimeter to centimeter, from millimeter cube to centimeter cube. So we're gonna convert this 10, we're gonna multiply times 10. This is to convert from the millimeter cube to the centimeter cube. Make sense? Then we're gonna find, if you did the multiplication here, the V1, we're gonna find it by 57,061.37, which is just like 0.4 centimeter cube. It should be centimeter cube. This is gonna be the first volume. Then you're gonna repeat again for the second volume. The second volume also, this is gonna be identical. It's gonna be the same. Also, it is still volume 2. The volume of a cylindrical shape with an internal hole. So it's going to be pi over 4, the external diameter, which is 250 square, negative the internal diameter, which is 50 square, times the height, which is 300. Then your objective is just to find or to use the equivalent values for these volumes. So I'm going to say that this is V2 bar, which stands for the volume of the product. Now I'm interested in the volume of the casting itself. So the volume of the mold cavity or the casting for that is equivalent to volume 2, it should be pi over 4. The 250 from the table, it is 255, and the 50 from the table, it is 40.8, right? So I'm gonna use this number in addition to the 300 that we used before. So it is 255 negative squared, 40.8 squared, and this should be multiplied times 316.2. Then do the calculation times 10 negative 3 to convert from the 10 millimeter to the millimeter cube to the centimeter cube. This is gonna give us the, if we did the calculations, so we got it by this value. Then we're gonna move to the third volume, which is V3 power, which is for this shape. For this shape also this cylinder with a thickness, with a height, so it's gonna be pi over 4, the external diameter which is 400 squared, negative the internal diameter which is 250 squared, times the height which is 80 times 10 negative 3, right? Just for the conversion. Then we have to use the equivalent one, which it should be the V3 equals to the pi over 4. The 400 from the table, we got it before by the 408, right? So it should be the 408 squared negative the 255. This is the equivalent value for the 250 squared, times the 80, which we got it before by the 81, I think, 0.6 here, right, from the table. So it should be the 81.6 times the 10 negative 3 to convert to the centimeter cube. If we did the calculations, we're gonna end up with the volume 3, right? So if we did here the calculation, so we got this V3, then we're gonna calculate the total volume, which should be the addition of the V1 plus V2 plus V3, which is gonna give us this value. Just add the 3 volume that you calculated. If you multiply this volume times the density of the steel that already given by 7.8 grams, it is already given up there by 7.8 grams over centimeter cube. So that's why we converted the volume into centimeter cube to have matching between the units, the different units, time 1.3. We said that we're gonna add 30% to calculate the gross mass. So this should be the gross mass, which G stands for the word gross. And if you calculate, we're gonna end up from the first calculation, we're gonna get the number, big number, a little bit number, indicate that this should be in grams. If you divide it by 1000, you're gonna find it by, or convert the unit into kilograms. It means that the gross weight of the molten metal that we have to use to fill into the mold cavity, it should be like around 1 ton, which is above 800 kilograms of molten metal that we should use for making this casting, right? So this is for the fifth step, is just to calculate the volume and then the gross mass of this casting. Then the sixth step, which is just move to calculate the flask design, which is step 6 here, the flask, just to find the flask dimension, the dimensions. Just to recommend a flask that we have to use for making this casting. And for this process, basically, we have to use, as we agreed, that we have to draw the 2 projections of the flask itself, or the mold, or like a tentative design of the mold, and we have to put some dimensions like A, B, and D dimensions, arrange them somehow, and then we're gonna use a table to come up with these values, or find the values of these dimensions that we're already adding. So if we did so, we're gonna find, you know, like the 2 projections already drawn here, that this is the casted product, right? This should be the molten metal, or the product, or the casting, where it is located inside the sand, and everywhere it should be the sand, and the exterior here it should be the flask, as we agreed before, right? And as you can see, there is a standing vertically the core itself. This should be in the thing in the middle, this should be the core, and these extra portions here, these are the core prints, right? And from our calculation, we find that this dimension is the H1 that we got from the table in the core design step by 70 millimeter, and the one on the top was the 0.6, the H1 that we got from the calculation before, right? Then this part on the top, this should be the coupe, and we should have here the drag. And this height, it should give us the height of the drag flask, and this should be the height of the coupe flask. And we are interested to calculating these 2 heights in addition to the width and the length, where we basically distribute some dimension. These dimensions are given here, the A dimension and A dimension, we said that the length of the column of the sand above the highest point of the casting, it should be A, or the highest point of the pattern, it should be A. In addition to the lowest point of the pattern in the bottom part, it should be also A. And this is it from the front view. In the side view, we have to distribute B, because the top view here, if we're gonna have a look, all of this casting will be seen like circular things. There are lots of circles here, right? The top view of this ship, because it is circular. We are not interested in the circle in the middle. We are interested in only one circle that gives us the largest dimension of the top view of this cast product, which is the 600. But from the table, we got the 600. It has two values, right? It has two values here. One value is the 634.7 and the other one is the 624.24, right? So pick the largest value here. Of all of these dimensions, the largest dimension is the 634, and should be the diameter for this one. It means that the biggest diameter here, it should be 634 millimeters. This should be the largest diameter. The previous number that was drawn was in the drawing, because I used a different draft allowance in this problem. I solved this problem before using a draft allowance of 2 degrees, but here in this video I'm using draft allowance of 1 degree, so that's why we have this difference in the number. But anyway, it is 634 according to our new calculations through this video, and we do have here B and B and B, and there should be the diameter. This should be the diameter of the down screw, and there should be a very squeezed distance, small distance between them, which it should be D. Then we do have another P from the other side. And the objective is just to find these values of A, B, and C, and D. I'm sorry. Find A, how much it is, how much is B, how much is D. We're gonna find these three values from the table. What is the table? This should be the table that should be provided for the flask dimension, which is this one, but you're gonna use the gross mass of the casting, that you're gonna use the G value that we got, but it should be in the kilograms. We got it above equals the 804 kilograms, right? So you're gonna ask yourself, is it up to 5 kilograms? Nope. Is it between 5 up to 10? Then find the range. We're gonna find that the 800 is located between the 500 and 1000 kilograms. It means that it is almost ton or above. So it is 800. So it should be located within this range. As you can see, we're gonna find the A value is 150, the B value it is 90, and the D value it is 120 millimeters. So we're gonna go up here and we're gonna write these values. A, we got it from the table by 150 millimeter, and the B we got it by 90 millimeter, while the D value we got it by this should be 90 millimeter, and this value is 120 millimeter. Then if I ask you how much is HC, HC should be the height of the cube. The height of the cube, it should equal to the A value plus this small little value that is located here, which is the 0.6 H1. And if you remember, we got H1 equal to 70 for the core design step. So this should be the A plus the 0.7 H1. So it means that we got the 150 plus the 0.7 times H1, which we got it by 70. If we did the calculations, we're gonna end up with 192 millimeter. This is for the HC. Then we have to use this value in terms of standard, right? But for now, just leave this value for now for the HC. Then do the same calculation for the H drag, for the drag part. The drag part, the total height here is 300, right? But this 300, this is what already in the product. This 300, it should be converted into its equivalent value that we got from the table of the pattern, which it should be 316.2, right? So this should be the total height. Then we're gonna add here the H1. Then we're gonna add A value to end up with the total height of the drag. So the drag height, it should be the 300. It should be the 316.2 plus the H1 plus the A value, right? So this is gonna give us 316.2 plus the H1, which we got it before by 70, plus the A, which is the 150, we got it from the table. If we did the calculations and we summed all of these values together, we're gonna end up with 536.2 millimeter. This should be the height of the jack. So have a look to these two heights. We don't have, this indicate that we have to use a flask with two different pieces or two different parts in such a way that the coupe, it has a height that is different than the jack. We can proceed with this option that you're gonna have a hybrid flask, kind of like the coupe has a height that is different than the height of the jack. Or in many cases, the flasks, they should, the two pieces of the flasks are identical or should be the same height. You probably, for some reason, you won't gonna have found in the foundry that you're already working in that we don't have a flask with these hybrid things or two different heights. So in this case, we have to use only one height for both of them. And this one height, it should be the biggest one, because if you use the H1, HC for both, you're gonna end up with a weak flask that can be easily broken, and even it won't gonna work because the total height is 300. Here we got the HC, it is 192 millimeter. It means that we have to use the largest height for both of them, and this is what I'm gonna do. I'm gonna use the total height that I'm gonna assume or consider that HC equal HD. I'm gonna use the big value here. The biggest value is 500 and something, right? It is above 500 millimeter. Then we have to convert it into the standard. If you remember the standard for the heights, it works from the 20, then we do have 40 or 30, then 40, and so on, it jump. So there is a standard value or a standard range. From this standard, we're gonna come up with the height as 550 millimeter as a total height for both the coupe and the jack. This is the standard one, according to the standard value, okay? So this is for the height. How about the width and the length? We're gonna do the same. So if I ask you how much is the width it should be B plus the 634 plus another B, and the B we got it here from the table by 90 millimeters. So what does it mean? It means that the total width, the W, were equal to 2B plus the 634 millimeter. If you did the calculation, and you should understand this should be 90 millimeter for the B plus the 634. If we did the calculations, we're gonna end up with 180 plus the 634. This gives us 814 millimeter. According to the standard, this is gonna give us a 900 millimeter width, because beyond the 5 millimeter in the standard for the width and the length, you're gonna use a step of 100. So there is 800 millimeter width and there is 900, but there is no 814 or 850. So this is gonna be the standard width. How about the length? We're gonna do the same calculation for the length. The length we do have 1B from the left, then DS, then D, then the 634, and another B from the right side. So we're gonna have in total 2B plus the DS, which is the diameter of the down screw, and we said that we have no clue how much of this diameter in addition to the small d in addition to the 634. So, and we got the D from the table by 120 and the B by 90. So this is gonna be 2 times 90 plus the 120, I'm sorry, the DS is unknown, plus the D small, which is just 120 plus the 634. If we did the calculations, we're gonna end up with plus the 120. This is gonna give us the 934 plus the diameter of the down screw. We said that in this step, we're gonna find the length of the flask in terms of the diameter of the down screw. This should be the sprue diameter. This is the sprue diameter. We're gonna find this length in terms of the diameter of the down screw. Then once we finish the calculation of the down screw diameter, we're gonna plug it here to come up with the length of the flask. Make sense? So, and that's it for this step. We already came with the suitable dimensions of the flask. In terms of the height, we're gonna assume that we're gonna use both heights, the same flasks for the cube and the drag with the same height, which is 550 millimeter, and the width it should be 900 millimeter. We're still waiting for the diameter of the sprue to calculate the length of the flask. Make sense? So this is for the fifth, or the step number 6, I believe. Then we're gonna move to the next step, which is step 7 for the calculation of the ingot or the gate. So step 7, we're gonna work here on the gating system. So calculate the gate diameter. How we can calculate the gate diameter? We said that there is an equation that we have, or formula that we have to plug in, which is the area of the ingot or the gate equals the G, which is the gross weight, divided by the rho, which is the density of the steel, times the pouring time, times the nu, which is the coefficient of friction, times the square root of the 2gh. What is h? It should be the effective height. So to plug into this data, basically, we have to calculate first h. We have everything except the h, which is the effective height. What is the effective height? As we discussed, this h. So let us calculate h. It should be the h, which is the height of the cube, negative the p square. This should be divided by the 2c. What is c and b square? We said that the c, it should be the total height of the molten metal, not the total height of the pattern. So if I ask you here, what should be c? C, it should be the total height of the molten metal, which it should be the 316.2. Don't include these two core prints into this total height. Here I'm talking about the total height of the molten metal, and this total height of the molten metal will be definitely this part. So this should be C. But how about P? The P, it should be the height of the molten metal above the parting surface. Do we have any molten metal above the parting surface here in this case? No, we don't have anything. It means that P, it should be 0 in this case. So we already have P equals 0. So P equals 0 because there is no height. If you refer to the previous videos, you're gonna understand these points very clear. So it means that we already have P equals 0. We don't have a value for C, but this term anyway will be eliminated. So we're gonna end up with 550 millimeter. Then your objective is just to divide by 10 to convert from millimeter to centimeter. So it's gonna be 55 centimeter. Make sense? The objective is just to have consistent units. So to achieve this, first of all, you should have the h. I'm gonna write down the units now. So h, it should be in centimeters. So that's why I divided by the 10 to convert from millimeter to centimeter. Then, how about the units in general? To end up with the area of the ingot or the ingot area or the gate area in terms of centimeter square, because it is area. To end up with centimeter square, we should substitute for the gross mass by grams, and the mass density should be gram over centimeter cube, and this should be seconds because there is a pouring time, and this dimension, this mu is a dimensionless. In addition to this should be 981. We knew that the gravitational acceleration should be 9.81 in terms of meter of second square, but we're gonna convert this one as well into centimeter per second square. So that's why we're gonna have the multiplication here times 10, but under the square root it will be 100 because we're gonna multiply times 10 under the square root. So it's gonna be like 981 substitute by 981 directly, and this should be centimeter as we got here, right? So that's why once you calculate h, divide by 10 to convert into centimeter, plug into here, and you should use for the gravitational acceleration 981, and the second and the gram per centimeter cube, as the density in many of the cases will be provided in gram per centimeter cube, and the gross weight, it should be in grams. You're gonna directly end up with the ingot area in centimeter square. Make sense? If we did the calculation, just do the substitution. So we're gonna end up with the area of the Ingot were equal to, we got the 804, right, for the gross mass, so we're gonna multiply times 10 power 3 to convert from kilograms to grams, divided by the density. The density is already given by 700.8 times the pouring time. The pouring time, as we mentioned, T, it should equal to T, the pouring time, it should equal to the S square root of G. But remember, for the calculation of this one, G here, it should be in terms of the kilograms. It should be in terms of kilograms, and this is the S that it is already given up there by 2. It is given. And G here, it should be kilograms. You have to stick to these units, right? Because this is like an empirical formula, which is commonly known for S square root of G for steel. We said that for any other material, you'd have another formula. So stick to the dimensions. It means that G, it should be in kilograms. If we did the calculation, this is going to give us 2 square root of 804. If we did the calculation, we're going to end up with a value in terms of seconds. This is going to give us the pouring time, how much it is, right? So we're going to find it by the square root of 804 times 2. This will be the 56.7 seconds. Then we're going to plug this value as it is into here. So it's going to be 56.7 times the mu, which is the coefficient of friction, which is already given by 0.3 times the square root of the 2 times 981 times the h that we got it by 55. If we did the calculations, these calculations, we're gonna find the ingot area in terms of centimeter square. And that's it for this step. Then, so we got the area, and the last thing that we have to do is to find the diameter of the ingot, how much it is. It should be the square root of 4 over pi times the area ingot that we just calculated. If you did the calculations, we're gonna end up with 4.84 centimeter as the diameter of the ingot. So if we use like 4.84 or 85 even, it is acceptable for the diameter of the ingot. Make sense? Then the next step is just to find the dimensions of the, calculate the runner dimension, and this is gonna be step 8. Find or calculate the runner dimensions. We said that the runner, according to the standard, it should have a trapezoidal shape in this way. So it should be of this form, has a big width, and there is a small width on the top, and there is a certain height, right? Okay, so, and for the calculation of the runner, we need a table. So the area of, to use this table, I've brought the table here to come up with this dimension, but to use this table, we need the cross-sectional area of the runner. And we said that this depends on the area of the runner that is related to the area of the ingot that we just calculated above here, which we got by 18.44 centimeter square. For the ingot, for the area of the runner, the same thing for the sprue, the area of the sprue, both are related to the ingot area through some fractions or percents. This basically depends on the, whatever we are going to pour the liquid metal to fill into the mold cavity under pressure or with non-pressurized. It means that depend on your design of the gearing system, do you need a pressurized gearing system or non-pressurized? In case that it is not specified in the problem, and in many cases, especially with the steel, it is preferred to work with pressurized gearing system. So let us assume that we're gonna use pressurized gearing system. So in this case, for pressurized gearing system, as we mentioned in the previous video, we can have like this ratio between the area of ingot and the area of the runner to the area of the down sprue. That this ratio should be 0.5, and here we then have the to 0.75 to 1. But in case that we do have non-pressurized, we're gonna have 2 to 1, right? The area of the ingot we calculated by the 18.44, and we have no clue how much is the area of the runner, how much is the area of the down sprue. So if you did cross multiplication, we can come up with the area of the runner. So the area of the runner will be, just do the multiplication in this way, like it's gonna be 0.75 times the 18.44 divided by the 0.5. This is gonna give us something in centimeter square, right? Why centimeter square? Because we're still working in the centimeter. So this is gonna give us 75 times 18.44 divided by 0.5 gives us the 27.66. Make sense? So this is for the area of the ingot. Then we're gonna use this area for the runner. We're gonna use this area. Is it up to 2 centimeters square? No, you're gonna find that it should be like up to, it is between the range of 25 up to 40. It means that it should be within this range. So it is up to, so here we are talking about up to 25. Is it up to 25? No. Is it up to 40? Yes, it is up to 40. So I'm gonna use this row, right? This row, we do have these 3 values. This should be the runner bottom width, which it should be the 60, and the runner height, it should be 73, and the top width, it should be lower, it should be 49. So we're gonna have here on the top 49 millimeter. It should understand that these units are in millimeter, and the bottom width, we already got it by 60, and the height is 73, and this should be 60 millimeter and millimeter. So these are the dimensions of the runner, and that's it for this step. Then we're gonna move to the step 9, which is related to the down sprue. We're gonna work on the calculation of the down sprue diameter. So calculate the down sprue diameters. So for the calculation of the down sprue diameter, we need the area of the sprue that we already skipped here, right? So now we're gonna do the multiplication of 1 times 18.44 divided by 0.5 to end up with the area of the down sprue. But you should understand that this area is the area of the down sprue from the bottom. You should understand that the down sprue, it has taper shape, so it has 2 areas, right? One from the top, and there is another area from the bottom. So this is the bottom area, and this should be the top of the down sprue. This is the sprue. Make sense? So the area of the down sprue that we're gonna get from up there, it should be the area of the ingot, which it should be 1 time the area of the ingot. This should be divided by 0.5. So it's gonna be the 18.44 divided by 0.5. This is gonna give us the 18.44 times 2, which will be equal to the 36.88 centimeter square. This is the area of the down sprue from the bottom. All right. So if I ask you how much is the diameter of the down sprue, the diameter of the down sprue from the bottom area, it should be the square root of the 4 times the area of the sprue from the bottom over pi, right? If we did the calculations, we're gonna end up with something like 6.8 centimeters. So it's gonna be times the 4 divided by the 0 pi square root equal to the 6.85 centimeter. This is gonna be the diameter of the down sprue from the bottom. How about the diameter of the down sprue from the top? There is a relation between the area of the down sprue at the top equals the area of the down sprue at the bottom times the square root of h over ht, as we discussed right before in the previous video. So this h should be the height of the cube. This h should be like hc, the height of the cube, divided by the ht, and ht should be the boring cup height. It should be like the boring cup height, which we said that in case that it is not given, we can assume that its value as 50, right? But it should be like 50 millimeters. So this, we can assume that this is 50 millimeter. So we should have the cube height as we got it by 550 millimeter. above. We got so it should have some consistency in the units like 2 millimeters, but that is fine to have because this is going to be ratios. That is fine to have this one as in centimeter. So if we did the calculations here, we do have this area, we got it by 36 point something here, right? 0.88. If we did the calculations, we're gonna end up with 55 over 50 square root times the 36.66, 88. This gives 122.3 centimeter square. Then we can calculate the diameter of the down sprue. The diameter of the down sprue from the top, which gonna give us the square root of the 4 times the area of the down sprue from the top over pi. If we did the calculations over pi square root, this gives us the 12.5 centimeter. It means that the diameter of the down sprue from the top, it should be like around 12.5 centimeter, and from the bottom it should be around 6.85 millimeter. Make sense? Then once we finish, should be the last step. The last thing that you have to mention here, you have to confirm the flask dimensions at the end. So this is the last thing, like you have to mention what are the flask dimensions, right? That should be used. So the flask dimension, we calculated the height of the coat is equal to the height of the drag, equal 550 millimeter. Also, we calculated the width by the 900 millimeter, right? But how about the length? The length, it was, if we gonna go up, it was like 900 and something, right? We got it here in terms of the diameter. It was 934 plus the DS. The DS, which DS? This should be the bottom diameter. The bottom diameter, not the top diameter, because this is this length, it depends on the bottom diameter. So we're gonna add the bottom diameter that we calculated. It should be the 934 plus the DS bottom. It should be the bottom one. So it's gonna be 934 plus the bottom diameter that we got by 6.85 here. So it's gonna be the 6 times 6.85. If we did the calculations, this is gonna give us like around 1,000. So it's gonna be like how much is gonna be like 30 plus 6.8. No, I'm sorry, this should be multiplied times 10 because this one is millimeter and this one is centimeter. So I have to multiply times 10 to convert the unit. So we're gonna have here 934 plus the 68.5. So this is gonna give us the 1002.5. The next value of the standard is 1100 millimeter length. So these are the standard dimension in terms of length, width, and height of the flask. And that's it for this problem. So we applied the 9th step, and as we agreed before, we skipped the 10th step, which is related to the riser design. It means that the next thing that we have to work over the riser design, but we gonna, as we mentioned, that we're gonna consider this one in a separate study. So yeah, as we mentioned, in the next videos we're gonna work on the riser design and the buoyancy force calculations. This it will be considered in a separate study, as I mentioned. So this is for this example, and that's it for this video. In the next video, I'm gonna try to solve another problem, one more example, in case that we do have like 2 projections of the casting. So it's gonna be the same procedure, the same steps and the same calculations. The key idea here that you have to practice a lot over this procedure to make it easy for you to hack this type of problem. All right. So thank you and see you in the next video.